Okay guys, so as promised I said I'd record the first lesson for you since I didn't get a chance to record it in last. So here is a review of what we did in the first lesson. So to start off, I'm just going to tell you what the learning outcomes are from the syllabus for this particular lesson. So first, explain that physical quantities have a magnitude and a unit. Then secondly, use the units named in the syllabus. And thirdly, use prefixes to indicate decimal multiples and submultiples of units. Okay, so we'll start off with the International System of Units. So, definition, what is the International System of Units? The International System of Units, known as SI for short, is the agreed units of measurement used around the world. There are 7 base units to the SI system of measurements. So in other words, the SI system is a globally agreed system of measurements, and you'd be very familiar with these units, these measurements, meters, kilograms, kilometers. All of these are examples of SI units that you would use in day-to-day life. So kilogram is the first one of the 7 base units, and kilogram is used to measure mass, and mass can be written shortly as a capital M in these square brackets. Mass is what's called a fundamental dimension, meaning it's really a key dimension or a very important dimension. That's not so important or something that you need to worry about. What you really need to know is that kilogram measures mass, and you can also represent mass with a capital M inside these square brackets. The next unit is the meter, which is represented by a small m, and it measures length, and length can be represented by this capital L in square brackets. And this is also a fundamental dimension. Next is the second, represented by S, and this measures, of course, time, and the dimension time can be represented by capital T in the square brackets also, and this is also a fundamental dimension. The amp, represented by a capital A, it measures electric current, and electric current, the dimension is this represented by this capital I in the square brackets again. Kelvin, capital K, and this measures temperature, and temperature's dimension is denoted by this theta inside the square brackets. Candela, CD, and this is luminous intensity. The unit dimensionality is represented by capital J in the square brackets. So this one maybe is not so familiar to you, and it's to deal with brightness. Mole, MOL for short, it's an amount of substance, and the unit is the capital N inside square brackets. Now there's a very useful idea called the great principle of similitude, and this is actually something that you might already know or have been told about in some form or another as early as elementary school. And the key ideas in this principle are as follows. You are only allowed to add or subtract quantities with the same dimensions. An equation must have the same dimensions on both sides, and you are allowed to multiply or divide quantities with different dimensions. So let's have a couple of examples here to explain these 3 ideas. So you can add 3 meters and 4 meters together, but not 3 meters and 4 kilograms. So 3 and 4 meters are fine to be added together because they're the same unit, the same dimension, but not 3 meters and 4 kilograms because they are different units and different dimensions. If A equals B and B is measured in meters, then A must be in meters too. And example number 3, distance travelled over time, so distance divided by time, is speed. The unit of distance is meter and the unit of time is seconds. So the unit of speed is meters per second, or meters over second. Now we'll look at prefixes, and prefixes can be used to make our units bigger or smaller depending on what type of problems we're dealing with. So here is the table of prefixes. Pico, represented by P, and it's 10 to the minus 12 factor. Nano is N, and it's 10 to the minus 9 factor. Micro is mu, and it's 10 to the minus 6. Milli is M, and it's 10 to the minus 3. Centi is C, and it's 10 to the minus 2. Deca is D, and it's 10 to the minus 1. Deca is dA, and it's 10 to the 1. Hecto is H, and it's 10 to the 2. Kilo is K, and it's 10 to the 3. Mega is capital M, and it's 10 to the 6. Giga is capital G, and it's 10 to the 9. And tera, capital T, 10 to the 12. Now, some of these you've seen before. For example, kilogram is a familiar one, as is centimeter or kilometer and so on. The bigger ones would be familiar too for using your hard drive. For example, terabyte, gigabyte, megabyte, kilobyte, and so on and so on. You are free to make any units, any size you want using these. So for example, there's terabyte, gigabyte, megabyte, and kilobyte. But of course, if you wanted to, you could have hectobyte or decabyte. Or for example, meters, you could have nanometer, micrometer, millimeter, which you would know too. So you're quite free to put these prefixes on any of the units really that we've just seen. So just again, for example, kg means 1000 g, or kilogram means 1000 grams, or μm, micrometer, which would mean a millionth of a meter. Okay, let's have a look at an example question. Suppose S measures some amount of length, M some amount of mass, and T some amount of time. What is the dimension of K in the equation below? What units could you use? So our equation is M times S over T squared equals minus KS. So let's have a look here at what the units for K is and what the dimension for K is. So we need to look at the dimensions of each term. So there's our formula, and I will look at each dimension of each term individually. So it's the dimension of the M times the dimension of the S over the dimension of the T squared equals the dimension of the minus 1 times the dimension of the K times the dimension of the S. The dimension of the M is mass, and the dimension of the S is length, and the dimension of the T is time. The dimension of the minus 1 is nothing. It has no dimension. It's just the number minus 1. It's not a measurement of anything, so you can forget that. And the dimension of K is what we're looking for, so I'll just leave that as a question mark. And the dimension of S is length again. Now you notice just like in maths, you can cancel on both sides here. So both those L's can be cancelled, and you're left with m over t squared, or mass over time squared, is the dimension that we're looking for. So in other words, the dimension of K is mass per time squared. You could use the unit kilograms per second squared as an example. Just to clear up any confusion here at the end, there is a slight, well, an important difference between dimension and unit. Unit is what we use in day-to-day life, so to speak, to make a measurement. For example, meters would be a unit. Dimension is more the idea of what we're measuring. So for example, length. So if the dimension is length, the unit is meters. So if we were talking about the height of someone, the dimension is a length, because that's the idea, so to speak, but the unit, what we actually use to make the measurement, would be meters. If something doesn't have a unit, we say it's dimensionless. So for example, in this question here, I had a -1, and that wasn't measuring anything. There was no units involved, so we could say that the -1 is dimensionless. We will talk about these units in more detail later as we come across them, but for now the two key ideas here are dimensions and units, and how they behave, and how you can treat them, and how you can deal with them.